All right, so this video is going to talk about a couple of different concepts that are related to each other. One is how the electrons in a covalent bond are not shared equally, so the bond is polar. That is to say, there's more electrons being shared on one side than the other. And the reason that they're not being shared equally is that one of the atoms is going to be more electronegative than the other. Electronegative means a tendency to draw electrons to itself and to be more negative. All right, now you have to realize this is a relative sort of thing. So I might be strong compared to a 2-year-old, but compared to a football player, not so strong. So it's a relative thing. You have to look at the electronegativity of both atoms to decide which side wins this pulling contest for the electrons. All right, so there is simply a rule. So when you look at the periodic table, some little bumps and stuff like this. Noble gases, well, up here in this corner is the strongest of them all. It's fluorine. Right? So the noble gases don't want any more electrons. They already have 8, so they're right out of this idea entirely. They don't form bonds for the most part. Down in this corner is the very weakest. Cesium, or francium, actually, I think is even below that. And so the further you are toward this corner, the more likely you are to be positive, and the higher you're up in that corner, the more likely you are to be negative. Now, generally speaking, there's a dividing line between the elements that are non-metallic and also tend to be very electronegative, whereas most of the elements on this side of the dividing line tend to lose electrons in ionic compounds. All right, so we're going to go and describe the bonding from a range of complete transfer of electrons to form ions, all the way up to completely equal sharing of electrons. Okay, so there is just a table in your book, and that's the table we're going to use, that actually have numerical values for electronegativity for every element. And to look at the difference in a bond, all you have to do is look up the numbers for the two elements and figure out what they are. All right, so we're going to look at a bond between, let's see, potassium and nitrogen. Okay, so we look up potassium's number in this table, and it is 0.8. And then we look up nitrogen's number in this electronegativity table, and we see it's 3.0. Okay, so nitrogen is very much more electronegative than potassium. And so that means this is going to be partly negative or maybe even completely negative. So the delta symbol means partially. And so this is going to be positive because it's losing the electrons that are being shared or transferred. All right, and so the difference in the electronegativity, which I'll abbreviate En, is 2.2. Okay, so when we have a difference of electronegativity of 1.8 or higher, that is going to be typical of an ionic bond. That is to say, it's not even shared electrons. It's K+, and we know that potassium likes to be K+. And then nitrogen, well, when we look at the anion of nitrogen, it really wants to be 3-. So what that tells us is, you know, 1 potassium is not going to be enough to donate 3 electrons to nitrogen. You need 2 more potassiums. So K+ and another K+. Each one transfers an electron to nitrogen, and you make nitride. And so you have an ionic compound, K3N. Of course, you recognize it ionic because potassium is one of the metals. It's from this side of the staircase, and nitrogen is a nonmetal. It's on the other side of the staircase. And when you have a metal and a nonmetal, you're going to have an ionic bond. Okay, and the reason for that is because the electronegativities are so small over here and so large over here. The difference is large, and you have an ionic bond. Okay, so next we're going to look at another possible shared bond, or maybe it's ionic. We don't know until we actually look. NO. So if you have an NO bond, you look up nitrogen, and I'm going to write it down below this time, and oxygen. All right, so the difference is 0.3 0.5. Okay, so the textbook says when the electronegativity difference is between 0.4 and 1.8, that the electrons are shared, but it's polar. That's to say there's a significant shift of electrons to the more electronegative element. And that means that the oxygen will have a partial negative charge, the nitrogen will have a partial positive charge, but it's still shared, but just not shared equally. And the way we denote a polar covalent bond is with an arrow pointing along the direction of the bond, where the head of the arrow is pointing the direction the electrons are going. So we put the arrowhead on the end of the bond where it's partially negative, and put the other end, which is a little crosshatch to make it look like a plus sign, on the positive end of the bond. Okay, so this is a polar covalent bond. This was an ionic bond. All right, now we're going to look at chlorine. Okay, chlorine is one of the halogens, forms a diatomic molecule for the element. Well, I don't even have to look up the numbers. I know it's the same number, so the difference must be 0, no matter what that number is. So remember, it's a relative thing. So it could have been 0.8, or 4 and 4, or a million and a million. The difference is 0. Okay? And so there cannot be a positive end and a negative end, since both ends are identical to each other in the way they can pull electrons. So it's like a tug of war where, you know, both sides are equally matched and the electrons aren't moving at all. This is completely non-polar. There is no negative end, no positive end. All right, so when you have a polar bond, you have what's called a dipole moment. When you look at the molecule, you can see that it has a negative end and a positive end. But when you look at other molecules that don't have a negative end and a positive end, it's non-polar. All right, and then finally, one more example. HCl, hydrogen chloride. Okay, well, now there are different elements, so we have to look at the number. Hydrogen is 2.1. And chlorine is 3.0, I believe. Yes, it is. And the change, or the difference in electronegativity, is 0.9. So it is a polar covalent bond because it's between 0.4 and 1.8. And the negative end is the one with the higher electronegativity. And so the bond dipole, which I'm going to draw off to the side here since it's kind of crowded, will be pointing toward the chlorine atom. And so positive end at the hydrogen. So it's, the electrons are being pulled this way, so the arrow points that way. All right, well, that's it.